talk. She was our own student here, did her master's and PhD from here, and now she is. It's a pleasure to see as a mentor, to see her now emerged as uh, one of the leading researchers in the world. Uh, and her current focus is on bandits, and hopefully I don't know about the current work, but hopefully we'll get to learn a lot about bandits. And from my introduction I could see she has a knack of explaining things at a pedagogical level. So the hint to Adirupa is now, would ask you many questions, and
Yes.
it's 12:30 at night, but we'll not spare you for that.
Yeah, that would be
So
nice. I'll be happy if I get questions. That will be the best. Yeah.
okay, so now pressure is on the audience as well. So Adirupa, please take it from here.
Okay. Thank you, sir. Thank you so much for the overly exaggerated but very nice introduction. And yeah, it was. I really miss my days at my PhD days, especially at IISc, and I did it with Chiru sir and Aditya Gopalan from EC. So it was very lovely, very fond memories I have. Okay, so because we don't have much time, so let's just proceed with the current work. I work on bandits learning theory more generally, but recently I'm also working a little bit on federated learning, like this distributed optimization. And when we do distributed optimization, there comes this question of reducing the communication complexity and also like maintaining, preserving the privacy of the local server. So I have been also like working a little bit on those domains. But yeah, primarily I'm still working on learning bandits and reinforcement learning kind of topics. So the primary broad goal of my work has been mostly to design predictive models using machine learning algorithms, which are more aligned to human feedback. So I mean, I want to design systems to understand what users want. I want to like learn from the users of the systems, which are most likely are going to be humans. So I want to collect the what the humans like and want to like design predictive systems according to their needs or their requirements. That's the broad goal of machine learning or AI in general. So what is the big deal in this goal specifically? So let's start with some earlier prediction models. We all know there's this, say, spam classification. It's a very simple task. In the earlier days where we used to use machine learning techniques, say we have some context. That context is going to be the email that you have received, and then there is a prediction space, and the prediction space is kind of binary. In this case, it's just whether an email is a spam or not spam, so you can make it like a 0 1 kind of a label. And then comes this predictor. You have to design this predictor, which is a mapping from the context to your decision space. And one way to do it is just design some loss function. For example, say you already have some label data for a bunch of uh, emails that you have already, someone already have classified it as 0 or 1. So you design a loss function. So if you, for a new email, if you correctly classify a spam email as a spam email, you get a loss of 0. Similarly, if it is a clean and you also classify it as clean, you get a loss of 0. But if you misclassify it, you get a loss of 1. Okay, and that's like a 0 1 loss. You can actually relax it to something like more like differentiable losses. For example, hinge loss or logistic loss. You can smooth it out a bit and do empirical, minimize the empirical loss over your training data set on some hypothesis class. Um, you can come up with your favorite hypothesis class, whether it is a linear class of functions or whatever polynomial class of functions. You minimize the training loss, and essentially you have some predictor. You already have some predictor. That's how generally things used to work when systems are not so overly complicated. We know how to design this loss function, the loss minimization. We have a good predictor, good hypothesis class, and like training these algorithms are not much of a difficult task until the time that now we have started using this AI or machine learning systems in all kind of complex and very crucial day-to-day human human task or like human requirements, starting from healthcare to stock market prediction to autonomous driving, robotics, recommender systems, fraud detection, and all those recent madness around this large language models. All of these are actually examples of predictive prediction systems. All of them has some context and decision space, and we need to actually come up with predictive algorithms or like some intelligent system which maps this context to the predictions. But then a lot of problems are there because these tasks are not as easy as some binary classification or multi-class classification things. So let's say an example of recommender systems. This, suppose there's a new user and he recently logs in to YouTube. You have no data of this person, so he's the context, as if this person is the context, and your prediction space is the list of movies. So what YouTube or Netflix or whatever they will try to do is, once the context comes into the system, you will try to design, the goal is to design a prediction model that maps this context to the decision space, which is, say, a bunch of, you want to show them a ranking of movies, and say you want to maximize the click-through rate, or you want to maximize the retention time of the user. It is not very clear actually what you want to maximize. So as opposed to the spam classification problem, it's very clear that you want to like just label it correctly. But in these cases, many things are not very clear. So firstly, you don't have any offline data for this user because this is a new user who comes to your system. There is no training data really available to you. So based on what are you going to train this system? Next is, what is the definition of loss here? Like you predict some bunch of movies, the user will probably click on it, or he will not click on it, he might leave the system. Based on, it's not very clear how would you collect the data, and what would be a loss function. So if you are not very sure how to collect the data, who is going to label my predictions? So my predictions are going to be some bunch of movies. The user is probably going to like scan it, click on one of them, or just not even click on one of them. He might even leave the system. How do you interpret it as a label data? And then how do you design the loss function? How is your ranking performing? How did you perform in terms of the ranking? And then finally, yeah, go ahead.
Hi, I have a quick question. So you mentioned that the user is a context. So I'm guessing like some information about that context is available and some is not. So are we considering hidden variables, or just the variables that are available to us?
So you can consider that you have some features available for this user, say the demography or whatever, the age, and you have the entire feature of the user, say the past history, everything is available. I'm really not considering any hidden feature for now. I mean, you can.
Okay.
I think that I'm not very sure from what point of view you're asking this question. Why do you want to like categorize something as hidden features and something as observed
Right.
features?
Right. So for example, a user may not tell everything about themselves to YouTube when they're.
Okay.
Yeah. But
Okay.
that's fine. So we are not considering those variables. So that's okay.
Yeah, I mean, for now, actually, for the purpose of my talk, I'm not going to consider that. But I think that's a very interesting question. So, have you seen actually other bandits work? Maybe I should like take it later. But have you seen like other bandit works where, because in contextual bandits, generally people assume that the features are fully known. But are there also like scenarios where they consider that some of the features are known and some are hidden, and you're
Yes. Yes.
somehow, is
So
it like?
I think there's a version of linear contextual bandits for latent features as well. So
Oh, this. I see. Okay.
right.
Uh,
So please go ahead. Maybe we can
yeah,
consider
I
this.
think I think yeah, but I'm not really considering. So that hidden, there could be hidden features, but right now let's not focus on that.
Okay.
Um, so yeah, so the problem is there are several problems here. No offline data available. The loss is not very clear. The label data, it's not clear what is the label, what is like the data that we are going to collect from this user system interaction. So, and then finally, how are we going to design this prediction model? So let's just take a step back and see why are we facing these challenges when we are trying to design this, say, as something as simple as a movie recommender systems. Let's see, because the goal is to actually train the machines, mostly like how humans are going to decide. So say you are in charge of deciding movies, how would you actually do that? Let's just think from a human's point of view, how are we making the decisions? And let's just try to train our machines almost the same way that humans are making the decision. So many studies in psychology and neuroscience and human perception, they have established this fact that humans are much more comfortable in making decisions on relative scale, rather, or in a comparative scale rather than in absolute values. So for example, if you are commuting from your home to the office or some new place and the Google Maps is showing you some multiple routes, you are going to choose the route which you believe has low commute time, it has low congestion, it has nice neighborhood, etc. But you're not going to really score the different routes that Google Maps is showing you and then choose the route which has the highest score. You will just make a comparative decision actually. So you will kind of, yeah, I prefer route A over B and C because of so and so reasons. Similarly, for movies, suppose I ask you two different kind of questions. In Netflix, say I show you 5 movies and I tell you like, can you rate these movies on a scale of 0 to 10, which is more like an absolute score, or giving a reward or a loss to each of these movies, which is like a labeled loss, like a loss label, or kind of like a regression problem, you can think of it. Or I can just tell you that, well, you don't have to give me the scores, just tell me which is your favorite movie. So naturally, most of us will like the second option because that's much more easier for us to elicit, just to pick our favorite movie. Um, so what's happening in intuitively or inherently, what's happening is each of us, whenever we are trying to make a decision, we have some preference matrix in our head. So for example, for this movie example, say we have these are 5 movies. So the preference matrix is essentially a K cross K matrix, where K is the total number of items that we have in our decision space. Okay, so in this case, there are only 5 items. So the rows and the columns of this preference matrix are just the items, and each ijth entry of this preference matrix is just an indicator of with what probability I like ith entry over jth entry. So if this point is 0.05 for row 2 and column 4, this means that the user inherently likes the second item over the fourth item, or the second movie over the fourth movie, with some probability 0.58. So if you show them movie 2 and 4, these two simultaneously, possibly the user is going to play a Bernoulli coin with bias 0.58. And if it is 1, it will show that I like movie 2 over 4. And if it is 0, it will say I will like movie 4 over 2. So that's how maybe we can make the decision, because we are not always entirely sure. There can be some noise in our preference decision. But more or less, this is how maybe one way to model the human decisions in a relative scale. So this preference matrix is going to be some. I'm sorry.
So for all preferences ij probability of ij plus ji has to be 1. That's the only constraint.
Yeah, that's the only constraint. That's the only constraint I have. And so henceforth, the diagonals are always 0.5 because Pij is equal to Pji, and I'm not going to have any other assumption as of now on this preference matrix. I hope that is clear. So yeah, this is some more other examples where even if you go to the eye doctor, he will ask you like which of these lenses are making your vision the clearest. He will not ask you that just give a score to each of these lenses and then I'm going to assign you a lens. Just you have to tell just on a relative scale, oh, this is making my vision perfect. So we are much more comfortable thinking in a relative scale, and maybe that's how we should elicit the information from the users as well when we are designing these complex systems. And just to make people more interested here, many of you probably have already seen, so when this ChatGPT has been trained, it's also this language prediction / large language models. It's essentially also a predictive model which has a context, and the context is essentially the question that has been asked maybe, and the sequence of words that has already been output by the system. So that's like the context, and the task of the system is always to predict the next word. So that's like the prediction space is the bag of words, the all possible words available, and some part of ChatGPT. So initially they did some supervised learning to actually come up with some initial prediction models by the occurrences of words in all possible available documents in the internet. But then they actually fine-tuned the model further using human relative feedback from the humans, just to make sure that if the tone of the language is correct, if the sentence that the system outputs has the right tone, or it is like it's not using any vulgar sentences. So it uses human feedback to actually refine the predictive system. So learning with preferences has been used not only just in ChatGPT, but recently there has been a lot of interest in AI/ML literature to train robots or train different prediction models using preference feedback. So given that, yes.
So I was wondering whether there are versions of this problem where that matrix that you asked for is not fully available, and then you might have some sort of matrix completion based on
you will not
clustering.
have this matrix. Yeah. So we will not assume. So this all I meant was, because I haven't like introduced the problem, this matrix is completely not available to you. It's like you don't know anything, because this is the matrix that the user have inside their head. So I am the one who is going to recommend you movies, right? I'm the system. I'm going to recommend you movies. I have no idea what is the preference matrix you have inside your head. But as I in a sequential fashion, as I keep on showing you some movies, you will click on some movies, you will not click on some movies. I will try to estimate at least some part of this matrix, so that I can at least recommend a good movie. So the matrix is completely not known.
Okay.
Yeah, I mean, maybe I should just bear with me for a moment. I will introduce the problem more formally, and then it will be more clear what is known and what is not known and what is the objective. Okay, so in this talk, what we are going to do is say we have it's mostly like inspired from this problem of recommended systems, but it's not necessarily recommended systems. We can actually use this for any kind of personalized prediction tasks. So as a running example, we will consider this movie recommendation. So what we have done in this work is we will see through user preferences, how can we train a prediction model which will be also personalized. So depending on who is the user and who is the feature or the user coming to our system, we would like to recommend him items or movies based on their features, but we will only be learning from their preferences. And it's also like an online decision making task, because we don't have any offline data. So we'll try to learn it from the scratch, of course. But of course, it is also personalized. So if there are similar users, we probably won't have to learn it from the scratch. So that's what we will try to do in this talk, and we'll see how to design an optimal algorithm as well as computationally efficient algorithm. I mean, it's a regret-wise optimal as well as computationally efficient at the same time. This has been some work which I did with one of my colleagues at Microsoft New York City when I was a postdoc there. We have also some follow-up things on this. And this has been like an open problem, just to brag about it. This has been some open problem from my previous colleagues who are also at Microsoft since 2015 to come up with a simultaneously optimal algorithm as well as computationally efficient algorithm, which we sort of closed in this work. So let's go to the formal problem setup. I will introduce this setup a little more generally, and then we will consider a special case of it. We will call it Dueling Bandits. So let's first start with this problem setup of Battling Bandit. It's just a fancy name of saying it's an active learning framework from human preferences or just relative feedback. So because it's an active framework, so it has some phases or rounds. So at every round, the learner or the algorithm is supposed to select a subset of size, say m, and there are total k many number of decisions. So this k could be the total number of movies you have, in your pool of movies, or total number of words you have your bag of words, or whatever is your prediction task, total number of possible decisions. If it is an information document retrieval thing, all possible documents available, particular for search engines, etc. Every time you show them a bunch of m items, which could be m could be 3, 4, 10, some subsets, and upon that you get to see some noisy subset wise feedback of this subset. So the feedback could be just the best item of this subset, or maybe a ranking or a partial ranking of these items, or maybe like top 5 items. It can be like different ways, but you have to like give me some relative feedback about your preferences of this subset of items I'm showing it to you. So from a YouTube's point of view, if we take that example, at any point of time, the YouTube will recommend me a subset of videos. Say my m equal to 6, so YouTube is going to recommend me 6 videos. Whenever I log into YouTube, I will see 6 videos, and then basically the user, say Alice, she will probably click on one of those videos. So we'll get to know that, okay, maybe Alice likes this video over the other videos. Depending on that, I have to like do some bandit algorithm, some algorithm I have to apply, which will update my prediction rule. So depending on Alice's click data, I have to like update my prediction rule, and then the next time I again predict her subset of movies. Goal could be to converge to the top few items, or the best possible video, the movies or the videos that Alice will probably like to watch the most. So that could be like the objective, to recommend the top M favorite movies of Alice. To make things a little more simplified, let's assume that m equal to 2. In which case, we will study this as a dueling bandit problem, because m equal to 2, it's as if like the two items are dueling with each other. Duel means like they're fighting for the winner position. So this problem has been actually studied a lot in the literature. This was invented by Joachim and Isong from Cornell, in the Cornell University, for some information retrieval tasks back in 2009. And since then, this problem and several versions of this problem has been studied in the literature. So let's just understand the problem a little more formally for a little more simplified setup where m equal to 2. Although this battling setup has also been studied, we will not go into that setup for the time being. So
question.
Now, yes.
So just to clarify, you want to identify in a fixed time t the k best arms or movies.
Yeah, but the thing is, that could be like one potential objective. We are not restricting our objective to, so it very much depends on, based on your system needs, what you want to do. If it is clear to you what is the top, how do you define the top 6 items, you can probably make it as your objective. But if my preference matrix do not have this total ordering, all this ranking kind of structure in it, then the top 6 items are not very clear, right? So how do you define this top 10 movies or top 5 movies? Does that make sense what I'm saying? So that could be one potential objective.
So I'm still asking for the goal. Is it similar to some sort of pack objective or top K identification?
You can do whatever. So you can do whatever. People have studied pack and regret and everything, but for now we will actually focus on the regret objective. So, but again, the issue is we don't have any total ordering or this transitivity kind of assumption that if 1 beats 2 and 2 beats 3, then 1 beats 3. That might not actually happen, because users in real world, it's not ideal. So users might have different preference relations between the items. So it's not very clear when we say it's the best item, what is the best item? And that's actually one of the problems we will face here. So as we said, the preference matrix is there. So say this is the dueling bandit problem. Here at every round, it's again the active sequential learning game. But here at every round, we will select 2 arms instead of m, because m equal to 2. So the Netflix platform or the YouTube is actually like as if just showing you 2 movies, and Alice click on one of those movies. And how is this click data being generated? So we have to assume something, that how Alice is providing this feedback for us to give some theoretical guarantees. So we will assume that this is the preference matrix Alice has inside her head. This is her movie preferences. Say k equal to 5. There are only 5 movies. Of course, this preference matrix is not known. So every time, say you select 2 arms from this 5 arms, xt and yt. So xt is the left arm and yt is the right arm. So these are the two arm or the movies. In general, like we will call items as arms because that's like the common bandit terminology. Arms are like just like items in the decision space. So whenever you choose xt and yt, as if Alice goes to that particular entry of the preference matrix, say xt equal to 2 and yt equal to 4. So Alice goes to the 2/4 entry of the preference matrix, toss a Bernoulli coin, and whatever the outcome is, 0 and 1, she just predicts according to, I mean, as if that Bernoulli outcome is revealed to you. Or she will say like, I like 2/4, which means the outcome is 1. If she likes, Alice says that she likes 4/2, then it will be like 0. That's like the outcome. So you see this binary outcome. The one very popularly studied objective in Dueling Bandits has been to find the Condorcet winner. What is a Condorcet winner? A Condorcet winner is if your preference matrix has an item such that that item beats every other item with a probability more than 0.5. So we are convinced that every entry of this preference matrix is between 0 and 1 because every entry is a probability here. It's a probability by which I beats j. Suppose there exists an entry such that it consistently beats every other item with probability more than 0.5, which means on an expectation that item is on an expectation it is a winner over any other item in the decision space. So that could be like a potentially good item. Maybe one of your goal is to actually find that item or do a regret minimization with respect to keeping that as a benchmark. So this could be one potential definition of measuring the performance of the online learner here. It's an online process because it's an online, you learn, it's like a round-wise process and you try to measure your performance in every step. So let's try to see the first entry here in this regret. It says pi star xt, which means the probability by which your left arm is beaten by the best arm I star. So say I star is this Condorcet winner. So the probability by which your left arm is beaten by the best arm, the probability by which your right arm is beaten by the best arm, and this -half is just to make sure that you have the right origin. Because suppose if xt is actually equal to I star and yt is actually equal to I star, then this entry is going to be half, right? So, but you want to incur 0 regret. So that's why this correction is done. And then you just average the performance of left and the right arm. So there's a divide by 2 and you sum it over t rounds. That's your total cumulative regret. Does this regret make sense? Because we will develop based on this. So does this regret definition make sense? Questions?
I think and proceed. I think that
okay.
Proceed.
Okay. Okay. So I mean, if you have questions, let me know, because I think we will try to criticize this regret objective and we will develop based on this. So one of the criticism of this regret objective is, firstly, this I star is a fixed benchmark. It really does not depend on my choices of xt and yt. This I star might not even exist actually. What is this I star? So I'm saying there is a Condorcet winner, but there might not be any Condorcet winner. In which case, how would you choose your I star? More challenging question is, why would this preferences be stationary? So right now I'm assuming as if Alice is coming to my system and Alice keeps coming to my system for next capital T many number of rounds. But that's not a very good setup of the problem, because the preference matrix can actually change over time. It can be P1 for Alice, then P2 for Bob, and then P3 for whatever Michael. There can be different preferences. So we have to also change the preference matrices, and if the preference matrix is changing over time, the benchmark, the I star, should also change accordingly. And there is also no personalization, no contextualization happening. Like based on who is coming to my system, my preference matrix should change accordingly. So all of these things are not really taken into consideration in this classical dueling bandit objective. Though there has been a lot of work, but people actually came up with different notions of winners, and it's almost the same objective has been studied for different notions of winners. But the crux of the problem is the preferences should change and the benchmark should also change. For example, in YouTube, suppose in the first 4 time steps, these are the 4 characters who show up in my system. So my preference matrix is probably going to look like P1, P2, P3, P4, which are different for this 4 different users. And if I now write my regret objective, it does not make sense that I always compare my performance, compare the performance of XT and YT, my choices, with respect to a fixed benchmark. Because this fixed benchmark might not be a good item for any of the 4 preference matrices. So what could be a better objective, firstly, even before we go to the personalization? What could be a better objective? So a standard regret objective was actually so far just comparing us with respect to a fixed Condorcet winner or a fixed I star. So as if we are computing this quantity as the relative performance of left and right arm against a fixed benchmark over T rounds. How about we take this summation, this maximum thing inside the summation, which means that now I want to be competitive with respect to the best item, like the best competitor, the hardest competitor of XT and YT. It's much more stronger objective, because what I'm saying is at every round, when I choose XT and YT, as if God sees my choices XT and YT, and he also sees what is PT, and then God actually chooses this IT star, which is going to beat my XT and YT the most. Obviously, this is the most possible strongest objective you can come up with, but we will see there has been some problem with this regret objective. But before that, one thing to note, so far we have been talking about pairwise preference, the preference matrices, which has the structure which are in 0 and 1. If we do a simple transformation of this preference matrix, which is, say, we define P tilde. P tilde is kind of like 2P minus 1. So I do a simple linear transformation of my preference matrix. So every entry of this ijth entry of the preference matrix is just transformed to 2P ij minus 1. Obviously, the zeroth entry, all the 0 entries become minus 1. The 1 entries remains 1, and all the 0.5 entries become 0 in this preference matrix. Now I have a new preference matrix, which entries are in minus 1 to 1. And why do I need this interpretation? Because this interpretation means that it has a zero-sum interpretation. For those who are aware of the zero-sum games, probably from the game theory lessons we had, it has a zero-sum. So the winning probability of one player is, so if I say this entry, the probability by which player 1 wins over 2 is 0.06. But at the same time, the probability by which player 2 wins over 1 is minus 0.06. So the gain of the reward, gain of one player is essentially exactly equal to the loss of the other player, like the minus of the, so the total gain of the 2 players is exactly equal to 0 in all this possible choices. So that's why it has a zero-sum interpretation, zero-sum game interpretation. So any pairwise preference matrix can be seen as a zero-sum matrix. In fact, it's a symmetric zero-sum matrix. So this is going to be helpful because now we can talk about Nash equilibria of this preference matrix. And Nash equilibria exists for all zero-sum games. So we can actually make that as our benchmark. So, okay, so let's take this example. Say this could be a potential 1 preference matrix. So for those who know, this is basically the simple example of rock, paper, scissors. So as if the 3 items are rock, paper, and scissor, and you will see like rock beats paper, and then yeah, it's just, you can interpret it. The thing is, whatever regret I just defined here, when I put the max inside the summation, I can always show that if I just simply put the max inside the summation, I can always come up with preference matrices such that no matter what I choose as my XT and YT, there is always a choice for the adversary, so that when the adversary plays that as the IT star, because adversary sees my choices as well as the preference matrix, I always incur a constant regret at every round. You can always play with me, because the thing is, you can see the preference matrix and you can also see my choices. For example, if you play rock and paper, then the adversary, the IT star, will be probably paper. I think paper beats rock. Yeah. If you play rock and scissor, the adversary will play rock. if you play paper and Caesar, the adversary will play Caesar. So every time I will be losing by a additive constant of half. So the thing is, there is no hope for me to actually minimize that regret. The adversary can always make me incur order T regret. And when the regret is order T, that means your total cumulative performance is linear in terms of the time. So it is not really decaying with respect to time. That means you're not really converging to the best arm or whatever your potential best item is. Typically, the objective of bandit is like regret minimization in bandit is to come up with a regret which is sublinear in T. So this problem is hopeless. So what we can try to do a bit of a relaxation. Those who are aware of multi-arm bandits and EXP3 sort of algorithm, they might have seen it already. We will assume that the learner, whoever is the algorithm, he's allowed to randomize his action. So he can play random action XT and YT. So the XT YT comes from some probability distribution now. It could be some joint probability distribution over the pair of arms. And then the IT star, the adversary, is not able to see exactly the realized value of XT and YT. He can only probably see the randomization, PT. So IT star only depends on PT and also the actual preference matrix, but he cannot see the exact realization XT and YT. So this is a slightly relaxation of the earlier objective we saw, and the question is, can we minimize this regret, in fact? And the second question is, so far the preferences could have been fixed, but we also want to have user personalization in it. So the preference matrices should somehow be modeled as in terms of the feature of the users, which is kind of the personalization problem, and we haven't talked about it. If there are questions, let me know. I hope it is like not too technically, not too heavy. Okay, so how do we induce a user personalization in the preferences? So as we saw that, suppose the first four time steps of our game of movie recommendation, these 4 users show up. And as a system designer, I know their login ID, I know some user information. Say that information is captured as the feature C1, C2, C3, C4, and this entire feature is as if known to me. So I don't assume there is any hidden feature. I'm not trying to learn any hidden feature at this point. This entire feature is known, and assume that the preference matrices P1, P2 is actually some function of this features. This is some function f, but of course this f is something that I don't know what this f is. The best I can assume is there is a function class. Every function in this function class maps a context to a preference matrix, but I don't know exactly which function has been used. I only know the function class, the bigger function class. This is mostly studied as a realizability assumption of bandits. You might have heard of it. Okay, so this is how we incorporate the preferences as a function of user features. Now, let's try to solve the regret minimization problem on this with the best response regret, like with this IT star objective that we have wrote. Before that, there has been some past attempts to resolve this question. There has been this work by Dueling et al., and it's a called 2015 paper, where what they have done is they have assumed that there is a policy class. Okay, so what is a policy class? A policy class is a mapping from context to actions. So now my benchmark, earlier my benchmark was just IT star. Assume this benchmark is kind of a policy which sees the context and map it to an action. Okay. The regret that has been studied by this earlier 2015 work was they just tried to be comparative with respect to the best fixed policy in the hindsight. So instead of try to compete with respect to the best fixed action or best fixed arm I, they wanted to be comparative against the best fixed policy. And obviously the number of policies are huge. It's really depends on the total number of contexts and the actions. So for each single context, you can have k different policies. So it's basically the size of the policy class to the power of the number of actions. That's your total size of the context class to the power of k. Essentially, that's the size of the policy class. It could be very huge. They actually tried competing with respect to this huge policy class, and the inside the regret objective is exactly the same. So this is now ft is kind of the new preference matrix, because ft is kind of f of ct, and this is the adversary, or this is the benchmark. What the benchmark is playing, pi star of ct. This is the benchmarks of the best policy. Sorry. And xt is what the left arm is playing. Again, this is the benchmark the best policy is suggesting, and this yt is my right arm. And again, take the average performance. That's my policy regret. So the paper has been actually tried resolving the policy regret, although they could not provide simultaneously an optimal regret guarantee, which is also computationally efficient. So they gave two algorithms. One is computationally inefficient, which has the optimal regret guarantee, and they give another algorithm which is computationally inefficient, but it has the optimal regret guarantee. So basically, an inefficient algorithm with optimal regret guarantee, and an efficient algorithm with suboptimal regret guarantee, but they could not achieve simultaneously the best of both. In this work that I'm talking now, we are actually resolving a much more harder regret objective. It is the best response. So you can see that our regret objective is harder than this policy regret, because the policy is blind to the two actions that I have been playing. The policy's prediction is only depends on what the context CT is. But when I put this IT star inside the summation, my IT star not only sees the context, it also sees my two predictions, XT and YT, and then try to beat me the most. So whatever the policy regret is, my best response regret is always an upper bound on the policy regret. You can always prove this. So we are actually solving a harder objective, and what we want to do is we want to give a simultaneously optimal regret algorithm, which is also computationally efficient. Okay. This is just a proof that policy regret is upper bounded by the best response regret. Okay. So let's see how do we resolve this issue. There is some contextual bandits algorithm, which is exp4, which we already know it's inefficient, but we can make two exp4 algorithm compete with each other. One exp4 predicts the left arm, one exp4 predicts the right arm, and whichever wins gets a reward of 1, the other one gets a loss of 1. But this is inefficient. So because exp4 is inefficient, so this is runtime inefficient, though this has the optimal regret guarantee. But this is not a good idea. So the second attempt could be, if suppose I know this underlying mapping, this function f, which maps my context to the preferences. If suppose I somehow magically know this, then I'm good, because once I know the mapping, I already know the entire preference matrix, because the context is available to me. It's fully available to me. Because I don't know what this function f is, I can try to maybe estimate this function. So I can try to have some f hat, which is a good estimate of my function f, and try to maintain some UCB of this scores of the every ij entries according to this f hat estimate, and play optimistically. The issue is when we have a very general function class, like the function is beyond linear function class, it's very hard to know that how to maintain a UCB, entry-wise UCB for such general function classes. Basically, maintaining a UCB of this is very hard. So that's also a bad idea. But what we can try to do is, it's essentially kind of a regression problem, okay? Because we have this function class, we just have to figure out which is the right regressor here. We are given the function class actually, and we already have some data available to us. So at time t, we have seen the data, we have seen the context for all the previous rounds. We have seen the xt, yt, the two arm I have played, and we have also seen the prediction. So we can try to run some regression algorithm to fit, kind of like find the best fit of f. So we can assume that there is some regression function, and it gives us f hat, and then we try to find the Nash equilibrium of f hat, because f hat is kind of my preference matrix. F hat of CT is like my preference matrix. So once I have f hat, I can try to play the Nash equilibrium of this preference matrix. And Nash equilibrium is kind of, if the learner is playing from the Nash equilibrium, then no other opponent can beat me. So that's like, this is like kind of the definition of Nash equilibrium. Just to be more clear, so if f hat is the estimated preference matrix at time t, so f hat is essentially, f hat t is essentially f hat of ct. The ct is the context I have seen at time t. So f hat t is f hat of ct. We call pt as the Nash equilibrium if the left arm is chosen according to pt. Then no matter what you play in the right arm, the right arm can never beat the left arm. So the left arm is sort of playing a soft distribution over the actions, because Nash equilibrium need not be a fixed concentrate, like it's need not be as one hot vector. It's a distribution. It lies in the simplex. It need not be one hot. It can be a distribution over the arms. So whenever you are playing from the Nash equilibrium, no other fixed action can actually beat me. And if no other fixed action can beat me, no other soft action can also, like no other distribution of actions can also beat me. So in some sense, like if the algorithm can play actually from the Nash equilibrium, then it should have the zero regret. The only issue is we don't know what the f is, so we can't really play from the Nash equilibrium. We can at most play from the f hat, the Nash equilibrium of f hat, our estimated f. But the issue is then we are not really exploring enough. We can get stuck into some local minima if we just start playing from the Nash equilibrium. We might be just exploring one part of the preference matrix, and we are actually like overlooking the other parts and not estimating those entries enough. And maybe we are like overlooking the true best arm. So we have to just add a little bit of exploration here. So we keep the same left-hand side, which is the definition of the Nash equilibrium. We will try to find a PT which satisfies this, but we also add some exploration. What is this term? What is the second term that I have added here? It just says that it's like 1 by PT of I. So what is PT is a distribution over the arms, right? It just refrains me to assign a zero weight to any of the actions. So if I add a quantity like 1 by PTI, it will ensure that I have to assign at least some amount of weight to all the actions, because that will help me to explore play every action at least with some certain probability. That means I'm never like stopping to explore. I'm never like just focusing on one part of the preference matrix. I'm exploring every entry is enough. But again, this exploration should not be too high. This exploration should be like controlled exploration. So that's what this gamma parameters, all of this are doing. So if I do a 1 by PTI, obviously I can't make it less than 0 because PTI can be at most 1. So I can't really make it less than 0. But yeah, I can make it something like K by gamma, where gamma is some tunable parameter. So if I suppose can somehow find a preference, a distribution over the actions, which is almost has the property of the Nash equilibrium, but it also ensures that every arm is explored with certain probability. And this entire thing is like small. That means the PT actually satisfies both these properties with good amount of, good accuracy. Then probably we could be done. Okay, so that's essentially the intuitive idea how we came up with the solve this problem. Actually, we did some back engineering, like some back calculation to formulate this entire regret minimization problem as a game between the learner and the adversary. It's a min-max game between the learner and the adversary, and we can see for the worst possible adversary's choices, what could be the best possible action the learner could have played. And there we found that it has the similar property, like the property that I wrote in the earlier slide. We found that if we actually resolve this min-max game, it has the similar property. It hints us that we should solve this convex constraint optimization problem. It's basically a convex constraint satisfaction problem. So each of this, these are K equations here. Each of these equations are convex in P, because this term is linear and this term is convex. So this is actually convex constraint satisfaction problem. K such convex constraint satisfaction problem, and because it is convex problem, it should be easy to resolve, to find such P. And once we have found the P, we can just play from that P. So we actually resolved it with some min-max game between the learner and the adversary. But the intuitive idea is what I presented in the earlier slide. So the final algorithm is very easy. At every point of time, I use some regression oracle to kind of find the best possible FAT, best fit of FAT based on the past observations. And then given the FAT, I just try to find the PT which satisfies this K convex constraints. Because it's convex programming, it's efficiently solvable. And then I can just sample 2 points xt and yt from that distribution PT because it's nearly Nash equilibrium of FAT. And eventually FAT will be close to my true function f. So that's how I will eventually end up playing the Nash of the true f. That's how I will get a sublinear regret. So the regret guarantee of this algorithm looks something like square root of kt, which is actually the best. It's sublinear in t, it's t to the 1/2, so it's sublinear in t. It's square root kt times the performance of the regression oracle. So because we are using a regression oracle, you would want this regression oracle to perform not too badly. So the total online loss of the regression oracle should be also bounded. If this is like order t, then we are bad. But generally, if we have finite function classes, you can come up with this online regression oracles which regret is kind of like order of log of f, because we are also in the realizable setup. So, okay, moral of the story is it's like order of square root kt times the performance of the regression oracle. But as long as your function class is finite, or even if it is not finite, it's some RKHs, there has been earlier works where people have indulge into like finding optimal performing regression oracles for these function classes. So we just have to like use them as my black box depending on what my function class is, and that's my final regret guarantee. So yeah, so that's more or less it. I can also we can also extend it to subset-wise setup. Of course, we have to assume instead of pair-wise preferences, we have to assume some subset-wise preferences here, which is a little more tricky, but almost the similar ideas can be lifted if we use some structured subset-wise preference model like Plackett-Lewis or multinomial logit. It's not very hard. There has been a lot of active open questions on this field of research, like for this contextual dueling bandit or this contextual pairwise prediction problem, if you have infinite decision space, because so far we were just working with finite many number of arms, if you want to do some more budget constraint situations where suppose you're not allowed to play an arm for too many number of times, because you are maybe like if it is an ad placement kind of thing, you are not allowed to show the same ad many number of times because you have to pay also to this. The ad agency might not be willing to pay too much. Privacy and other trustworthy constraints that people have been studied so in the literature recently. So there are lots of open questions. There's also some work on the reinforcement learning scenario where the preferences actually depends on which state the user is in. This literature of learning with preferences in the reinforcement learning scenario has not been really studied much. It's really very understudied, especially the theoretical aspects of it. We have one work which appeared in last year AI stats, but it's like it has a lot of simplistic assumptions in it. So I'm really not going into it. Just to give a glimpse of, there is also this literature where people try to find the policy, like do the policy optimization and reinforcement learning with preference feedback. There the feedback is the preferences over the trajectories. So there are two trajectories instead of two movies. There are two trajectories, and some expert gives the idea that, oh, this trajectory is better than the other trajectory, and we want to learn the best policy from that in some sense. This is also a very open area of research because even less work has been done from a theoretical point of view, and it's much more harder actually to prove theoretical guarantees with preference feedback for reinforcement learning. So that's more or less what we have. We had started asking with some questions like what is the loss function, how do you collect the data. So we tried answering some of them. The loss function could be just training through preferences. We don't really have to define a loss function here. We can just do regret like train through preferences. We don't need a loss function. We can collect the data in terms of preferences. There's no offline data, but we can do an online training of the system, and then finally design an effective prediction algorithm, which we saw one thing, but it should change depending on what problem you're trying to solve. And yeah, mostly that's what I wanted to cover in that talk. I'm not even sure who are if you have questions, people are there still or not.
We are all here. Now
Okay.
The question is, it's 12, I think. Yeah, I think it's 1:30 now there, right?
Yes, it's 1:30.
I request all of you to send a lot of questions, but not now. To send it to her, and she will, Aadirupa will respond. It's 2 o'clock at night for 1:30 at night for her. So thank you, Aadirupa. But before that, I'm sorry, I'm stealing Rahul's thunder. Rahul should be doing all of this, but let's have only one question now, if you want to ask, and all the other questions can go to Aadirupa as email or as she feels. Anyone want to have one last question?
Maybe I did not make any sense.
No, it made a lot of sense. Actually, I scared them saying that it's 1:30. They are feeling bad for you now.
No.
And I think, yeah. So excellent work. I mean, so you also got to see some old results. We'll steal it from you now. Some results you're showing on the preparation and things like that.
Yeah, I mean, actually, to be honest, this problem, when I was at MSR, I worked on this problem. I felt like my lifespan reduced for 10 years. And now
Wow.
I'm trying to do like a follow-up of it. And I feel like that has reduced my lifespan for 20 years because I have been so frustrated with the problem. So we are using some online regression. We are trying to do some offline regression, like some technicality. It might not be very exciting in general, but it's very exciting, at least for me and Akshay, who was my co-author. And it's very hard, the problem. I mean, I have been trying since last 2.5 years and I could not resolve it. I mean, we are able to resolve some minor extensions here and there, but the main problem is we are not able to resolve it. But this problem is something is very close to, I mean, I really enjoyed working on this problem. And so, yeah, but it's just hard. Yeah. But if you have questions or you want to discuss something, I'm very excited about this problem in general. So I'll be very happy to answer anything or discuss more if you are interested.
Right. So maybe just all of you can write to Aadirupa as you feel like. So thank you, Aadirupa, again. We hope to hear you in person as soon as you are comfortable. All right.
Yeah.
So do take care. All right. So
Yes,
let's
sir.
close.
Yes, sir.
Yeah.
Okay.
Thanks for the talk. Very nice results.
Thanks.
Bye.
Thanks. Bye.